Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. We're still in chapter 4, the medium access control sublayer, which is a sublayer of the data link layer responsible for solving the multiple access problem. In a broadcast network, which is a network that has a shared communication channel or a shared communication medium used by all stations connected to the network, we get a problem that we call collision in case two or more stations attempt to transmit frames at the same time. Now, to avoid these collisions, we have to apply multiple access mechanisms, and this was the main topic of this chapter. In the previous video, we talked about Aloha protocols. Aloha protocols, whether pure Aloha or slotted Aloha, works as follows. If a station has a frame to send, it just sends the frame. If a collision happens, it will wait, the station will wait for a random amount of time and then retransmit the same frame again. If there is no collision, it means that the frame has been delivered successfully already. So, how can we significantly do better than this? This is basically the idea of today's lecture, the topic of today's lecture, and we would like to talk about carrier sense multiple access, or the CSMA protocols. Now, CSMA was invented after Aloha, still we would say long time ago, to the extent that it is part of the standard nowadays. So CSMA is part of the Ethernet standard. As we mentioned several times, Ethernet is a standard for building local area networks using cables. And as part of the Ethernet standard, we have the CSMA, the Carrier Sense Multiple Access Protocol. Now, what is Carrier Sense Multiple Access, and what is the main difference between CSMA and Aloha protocols? The main difference is as follows. As opposed to Aloha, in which stations just transmit if they have a frame to transmit, no, in CSMA, stations would listen for ongoing transmissions first. So if I'm a station and I have a frame that I want to transmit, before transmitting, I would listen for the channel, trying to detect any ongoing transmission. So that listening to the channel, this is what we call carrier sense. We try to sense if there is a carrier. In other words, we try to sense if there is an ongoing transmission, and we do that before we attempt to transmit ourselves. So this is the significant or the fundamental improvement as compared to Aloha. In Aloha, if you have something to send, you send. And then you just wait to see if there is a collision or not, and then you act accordingly. And if there is a collision, you would wait for a random amount of time and then retransmit. However, in carrier sense multiple access, in CSMA in general, if you have something to send, you would sense the channel first. You would sense the channel trying to detect any ongoing transmission, and then you would act accordingly. Now, how does CSMA operate exactly? We have three main flavors of CSMA. In other words, we have three main protocols that fall under the CSMA umbrella. The first one is called the one persistent carrier sense multiple access protocol, one persistent CSMA. How does that work? It works as follows. Let me explain how it works, and then I will go back to try to justify why the title is called one persistent. In one persistent CSMA, if a station has a frame to send, it would listen to the channel first, trying to detect an ongoing transmission. Now we have two cases here. We have two outcomes. Either we find the channel idle, so we find the channel empty and no one is sending at the moment. In that case, the station transmits. Or we find the channel busy. So if we can detect, after sensing the channel, if we can detect that there is an ongoing transmission, of course, there is no need to transmit because there will be a collision for sure. So in that case, the station will keep waiting, will keep sensing the channel continuously, waiting for the channel to become idle so that it starts transmitting immediately after the channel becomes idle. And this is basically the reason why we call it one persistent CSMA. So as you notice from how the protocol works, the station, in case it finds the channel busy, it will stay there, continuously sense the channel, waiting for the channel to be idle to start transmitting immediately. So that station is persistent in seizing the channel once it becomes idle for sure with probability 1. So there is no possibility that the station would basically back off and wait for random time and then come back to try again. That does not happen. So the station insists or persists on seizing, capturing the channel immediately after it becomes idle. As an analogy, imagine that you want to go shopping, you want to go to buy something, and then you go to the mall, to your favorite store, and you find the store closed. So what would you do in this case? In one persistent CSMA, you would wait in front of the store door, in front of the shop door, waiting for the shop to open. Once it opens, you enter immediately. So this is basically the analogy. Again, how does one persistent CSMA work? If a station has a frame to send, it will sense the channel. If the channel is found idle, the station will transmit immediately. If the channel is found busy, the station will continue sensing the channel so that after it becomes idle, it starts immediately transmitting. Now, after we do that, if a collision happens, so if the station does not get the acknowledgement, if a collision happens, it will wait for random time, and then it will come back to try over again by repeating the protocol. Sense the channel, idle, transmit, busy, wait there until it becomes idle, and then transmit. So in other words, how does this compare against Aloha? Did we reduce the number of collisions? Yes, we did reduce the number of collisions. Which collision is avoided if we compare against Aloha? We avoid the collision basically that would happen if there is someone already transmitting. So if there is someone already transmitting in the channel, in Aloha, I would just start transmitting because I have a frame, and then we get a collision for sure. So I have to wait for random time and then retransmit. However, in one persistent CSMA, since I sense the channel, because I sense the channel first, and in case I find it idle, I don't transmit. So that particular collision or that particular class of collisions is avoided. So that's why it is clear that one persistent CSMA performs better than Aloha. Since we have less, this is an intuitive argument. This is an intuitive argument. So since we are expecting less collisions, it means that the throughput, which is basically the average number of frames successfully delivered per unit time, is also higher. So the throughput is better than Aloha. Now, another question. So as opposed to Aloha, we have managed to reduce the number of collisions because we are sensing the channel. But question, are we avoiding collisions altogether? In other words, is it still possible to get a collision? Yes, it is still possible to get a collision. Imagine that we have two stations basically sensing the channel, and then they find it idle at the same time because the channel is idle. So there is no one transmitting at the moment, but we have two different stations who have frames to transmit. They sense the channel, they find it idle, they will send together, isn't it? So collisions are not avoided altogether. However, as compared to Aloha, as compared to the Aloha protocols, collisions are reduced. The number of collisions are reduced. That's why one persistent CSMA has a higher throughput than Aloha in general. Now, can we still do better than one persistent CSMA? Yes, by the second protocol, which is called non-persistent CSMA. Now, how does non-persistent CSMA work? If a station has something to send, if a station has a frame to send, it listens to the channel. It listens to the channel. And if the channel is idle, the station transmits. If the channel is busy, the station will not continue sensing. The station will just back off, wait for random time, and then come back to repeat the protocol over again. Repeat the protocol by starting with sensing the channel. By starting with sensing the channel. Okay, so let's compare this intuitively again versus one persistent carrier sense multiple access. So in non-persistent CSMA, and basically the name non-persistent comes from the fact that the stations are not persistent. The stations do not insist on capturing the channel after it becomes idle immediately. No, the stations go away. So if they find the channel busy, the stations would back off for random time and then come back later to start over again. As an analogy, if you want to go shopping, you go to your favorite shop, you find it closed. Instead of waiting at the door, as in one persistent CSMA, no, you go home, wait for random time, and then you come back to check if it's open or not. So this is basically the difference between one persistent and non-persistent CSMA. But going back to our question, did we avoid some collisions as compared to one persistent CSMA? Yes, we avoided the collision that could happen if two stations find the channel busy in one persistent CSMA. If two stations find the channel busy, what would they do? Both stations would continue sensing so that they would start together transmission at the same time immediately after the channel becomes idle. So the channel is busy. I'm sensing the channel because I have a frame to send. You are sensing the channel as well. It's a shared channel. You are sensing the channel also because you have a frame to send. Both of us find the channel busy because there is a third station having an ongoing transmission. Both of us will find it busy. However, both of us will continue waiting, and then after the channel becomes idle, both of us will start transmitting at the same time, which will lead to a collision. Now, that particular collision that happens in case two stations find the channel busy is avoided here, or is avoided with high probability. Why? Because in non-persistent CSMA, if we have two different stations sensing the channel and finding the channel busy, it's not likely that they will start transmitting at the same time, simply because both stations would stop and come back after a random amount of time. Since it is a random amount of time, it is not likely that they will come back to sense at the same time. It is likely that these two stations would come back to sense the channel at different times, so that collision is avoided here. Now, since we have a class of collisions avoided due to non-persistent CSMA in comparison to one persistent CSMA, since we have less collisions, we're also expecting a better channel utilization. So the throughput in terms of the number of successfully delivered frames is expected to be higher in non-persistent CSMA as compared to one persistent. But since the channels are basically going back, waiting for random time, coming back to check again, that's why we are also expecting longer delays. So this is the trade-off. Non-persistent CSMA leads to longer delays until the frame is delivered. Longer delays until the frame is delivered, but the overall throughput is also higher because we are avoiding some collisions. Finally, we have the third protocol, the third CSMA protocol, which is called P-persistent CSMA. Here, that P is a probability that will become clear after we start describing the protocol. How does P-persistent CSMA work? First of all, it applies to slotted channels. So for P-persistent CSMA, we assume that the channel is slotted. In other words, we assume that our time in general is divided into time slots, discrete time slots, and any transmission can start only at the beginning of a time slot. If I have a frame to send, I can send it only at the beginning of a time slot, not at any arbitrary time. So this is just a comment. This is just an assumption on the side. Now, how does P-persistent CSMA work? When a station has a frame to send, it senses the channel. As you have noticed, in all three CSMA protocols, we always start with sensing the channel, and this is the main difference between CSMA, regardless of which kind of CSMA, and Aloha. In Aloha, if we have a frame to send, we just send. So going back to P-persistent CSMA, if a station becomes ready, in other words, if a station has a frame that it needs to transmit, it will sense the channel. Now, for simplicity, let me start with the case that the channel is found busy. If the channel is found busy, of course, I don't have to transmit. So the station will wait until the next time slot according to the protocol. The station will wait until the next time slot, and then it tries again. What is the meaning of tries again? The meaning of tries again basically is I sense the channel. In the next time slot, I start over by sensing the channel. So if the channel is busy, wait until the next time slot and then try again. However, if the channel is idle, and this is the main difference between P-persistent and the previous two protocols. In the previous two protocols, if the channel is found idle, the station transmits. Of course, this can lead to a collision. If two stations are sensing at the same time and they find it idle at the same time, they would also start transmitting at the same time, collision, right? So in P-persistent, if the channel is found idle, I don't transmit for sure. The station transmits with probability P. Now, what does that mean? It means if the station is found idle, if the station senses the channel and finds the channel idle, the station would transmit only with a probability P. Of course, probabilities are between 0 and 1. In other words, the station does a probability test. The station does a probability test. If the probability test succeeds, it will transmit. If the probability test fails, it does not transmit, in attempt to reducing the collisions, in attempt to avoiding two different stations sending at the same time because they find the channel idle. Let me try to elaborate more on doing a probability test or sending with probability P. This is really equivalent to tossing a coin. Imagine that you are the station. Imagine that you are the station. You sense the channel and then you find the channel idle. You toss the coin. If you get heads, you transmit. If you get tails, you don't transmit. This is exactly equivalent to the station transmits with probability 0.5, because if you have a fair coin, then the probability of getting a head is 0.5 and the probability of getting a tail is also 0.5. So if we can imagine that we can design coins basically for which the probability of the head can be chosen as we want, if we can design a coin so that the probability of getting a head can be selected as we want. So a coin in which the probability of getting a head is 0.7 and the probability of getting a tail is 0.3. So basically that P is a parameter, and that CSMA protocol, it's a fixed probability which does not have to be 0.5. We can set it, of course, as we will see in the next slide here. We have basically a trade-off. If it's too small or too large, maybe it's not very good. However, in principle, we can choose the value of P, right? And to have a more general example, imagine that the station has a coin which gives you a probability of a head of 0.7 and the probability of getting a tail of 0.3. In that case, what does the station do? If the station finds the channel idle, it will toss the coin. If you get a head, which happens with probability 0.7, the station will transmit. If you get a tail, which happens obviously with probability 1 minus P, which is 0.3, the station will wait until the next time slot and then try again. Try again means sensing the channel again. Now, implementing that tossing the coin, obviously it can be done simply in software by generating a random number. So if I generate a number at random, let's say uniformly distributed between 0 and 1, and then I compare against the fixed probability. If my number is less than this value, I transmit. If the number I generate at random is more than this value, I don't transmit, and this is what we would like to do. I hope that you got this idea. So in short, if a station has a frame to send, when a station has a frame to send, it will sense the channel. If the channel is busy, the station will wait until the next time slot and then try again. Try again means starting from sensing the channel. However, if the channel is found idle, the station will transmit only with a probability P, which is a parameter, which means that with probability 1 minus P, the station will not transmit. And in this case, the station will simply wait until the next time slot and then try again. Now, what do you think will happen in the next time slot? In the next time slot, the station will sense the channel. If the channel is still idle, it will repeat the same probability test. It will still toss the coin. If we are successful, the station will transmit. If the station is not successful, it will wait until the next time slot and then sense the channel again. If it senses the channel again, obviously the channel is found idle or busy. If it's idle, do the probability test, toss the coin. If you're successful, send. If you're not successful, don't send, and so on. Obviously, this will keep going on. This will keep continuing until the station eventually transmits, because the probability test has succeeded, or maybe someone else has captured the channel. So when the station waits until the next time slot and then senses the channel, it will find the channel busy. In that case, the station will wait for random time and then it will try again. I hope you understood P persistent CSMA. If we recap, one persistent CSMA, the station that has a frame to send will sense the channel. If the channel is idle, transmit immediately. If the channel is busy, wait and continue sensing continuously. Start immediately after the channel becomes idle. This is one persistent. In non-persistent CSMA, sense the channel if you have a frame to transmit. If the channel is idle, transmit immediately. If the channel is busy, wait for random time, come back, start over again by listening to the channel. non-persistent CSMA. Finally, P-persistent CSMA, if you have a frame to send, sense the channel first. If you find the channel busy, wait until the next time slot and then try again. However, if the channel is idle, do a probability test. With some probability P, you transmit, which means automatically that with probability 1 minus P, you will not transmit. So although you found the channel idle, with some probability 1 minus P, you will not transmit. And in this case, you will defer. You will wait until the next time slot and then try again. By sensing the channel, this will keep going next time slot, until your probability test is successful. Or maybe although you started by finding the channel idle, but your probability test was unsuccessful, so that someone else started transmitting, and in this case, you will find the channel busy. Now, in that case, in which you find the channel busy after idle, you will wait for random time and then try over again. Now, carrier sense multiple access may come with an add-on, with an extra option that we call collision detection, and this is called CSMA/CD. So what is carrier sense multiple action with collision detection? Basically, that feature of collision detection can be added to any one of the 3 carrier sense multiple access protocols. So what is collision detection? In the normal CSMA protocol, if a station starts transmitting, it will not continue sensing. This is in the normal case. So I sense the channel, I find it idle, I start transmitting. I don't have to continue sensing. But if we apply CSMA with collision detection, that option, collision detection, simply means that if the station starts transmitting, whether it's P persistent or non-persistent or 1 persistent, if the station starts transmitting, it does not stop sensing the channel. The station continues sensing the channel even after it began to transmit. Why? Hoping to detect a collision in the middle of the frame. If it detects a collision in the middle of my frame, I don't have to finish it, which will improve the overall performance because I detect the collision in the middle of my frame. So instead of finishing the frame, waiting for the acknowledgement, no, I know early in the middle of the frame, I know about this collision, so I stop transmitting. Even further, the station that has done that can send a jamming signal on the network, which will be received by all other stations, knowing that there is a collision now, that there is an ongoing transmission now, so these stations would not start transmitting under any circumstance. So collision detection is an extra add-on, is an extra feature that can be added to any one of the 3 carrier sense multiple access protocols, and it simply states that if a station starts transmitting, it will continue sensing, so that if it detects a collision in the middle of the frame transmission, it will not finish the transmission, it will stop in the middle of the frame, send even a jamming signal so that everyone knows that there is an ongoing transmission, and this will improve the overall performance. Now, just a comment here. For collision detection to work, which is basically based on the fact, based on the ability of detecting a collision in the middle of the frame. For this to work successfully, frames cannot be too short. So that's why frames have a minimum size. If frames are too short, they need to be a little bit longer so that even the stations that are furthest away in the network can still detect collisions from each other in the middle of the frame transmission. So let me put things together here. This is just a comment on the limitation on the frame size. I just said that there is a lower limit on the frame size. In other words, frames cannot be too short. So that we can apply collision detection. So that any collision can get detected in the middle of the frame transmission, even if that other station that is transmitting at the same time is furthest away in the network. So that's why frames in general cannot be too short, or in other words, they have a lower limit on their size. Now, do frames or packets have a maximum limit on their size? Can they also not be too large? Yes, that's why we have packets in the first place. Why did we say in the introduction that if a message is too large, it is broken into smaller packets? This is done so that different stations, so that different users of the network are able to share the network resources, like the network bandwidth, in a fair way. Now, if packets are too large, it means one of the network users will capture that network for too long, avoiding other packets from being transmitted. But if my packet is small enough, it means that the network will carry my packet, followed by someone else's packet, followed by someone else's packet. So we would be sharing the network in a fair manner. So in short, putting things together, we have an upper limit or a maximum limit on the frame or packet size for fairness, for fair resource sharing or fair network resource sharing. At the same time, we have a lower limit on the frame size. Frames cannot be too short as well, so that collision detection works successfully. Now, this figure really summarizes the performance difference between all these protocols that we talked about in this video and in the previous video. So let's start with pure Aloha. And basically, we even derived this function completely. So this is the pure Aloha. On the x-axis, we have the number of attempts, average number of attempts per frame time, which is the offered load G. And on the y-axis, we have the throughput S, which is basically the average number of successful deliveries, the average number of successful deliveries, or the average number of successfully delivered frames per frame time. So throughput versus, offered load versus throughput, attempts versus successful deliveries. Pure Aloha, we had a throughput curve that goes up and comes down. Slotted Aloha was better than pure Aloha. So the maximum throughput of slotted Aloha was 36%, 0.36, but the maximum throughput for pure Aloha was only 0.18, so we had double the performance, and we talked about that in detail in the previous video. Now, in this lecture, in this video, we talked about CSMA protocols. One persistent CSMA works better than both Alohas, and we know that when we talked about one persistent CSMA, because simply one persistent CSMA avoids collisions as compared to Aloha, because we sense the channel. Now, let me skip for now for a few seconds the P persistent, 0.5 persistent, 0.1 and 0.01 persistent CSMA. That's all P persistent with different values of P. Let's move from one persistent to non-persistent CSMA. As you notice, in general, non-persistent has a higher throughput than one persistent CSMA. Why is that? Because, as we have explained, non-persistent CSMA avoids some extra collisions as compared to one persistent CSMA. It is those collisions that would happen if the channel is found busy by two stations at the same time. So if the channel is found busy by two stations at the same time, in one persistent, these two stations would keep waiting, and then they will start eventually transmitting together once they find the channel becoming idle. But in non-persistent, if two stations sense the channel and find it busy, they would both back off, wait for random times, and then come back possibly at different times to start over again by sensing the channel. So this is regarding a non-persistent. So as you notice, pure Aloha, slotted Aloha is better. One persistent is better. Non-persistent is even better in terms of the throughput. However, of course, as we have understood, non-persistent also comes with a delay problem. It has a longer delay. Now, it is best that we perhaps compare P persistent together, like P persistent with different values of P. 0.5 persistent, which is the P persistent protocol in which P is equal to 0.5, which means that if you find the channel idle, 50% chance you transmit, 50% chance you will wait until the next time slot, versus P persistent with P equal to 0.1. So when you find the channel idle, 10% chance you transmit, 90% chance you don't transmit and wait until the next time slot. 0.01 persistent means if the station finds the channel idle, 1% is the probability of sending, only 1%, and 99% of the time, 99% chance we will wait until the next time slot to try again. So what is the trade-off here? What is the effect of changing the value of P? If we reduce the value of P, what happens? What do you think happens? If P is 0.5 or 0.1 or 0.01, what is the effect? The effect is that we reduce the chance of sending if a station finds the channel idle, and thereby basically attempting to reduce the collisions as well. That's why we have the probability P in the first place. So if there is a 50% chance to transmit, it means that it is maybe likely that two stations would transmit at the same time. But if that probability P becomes 10%, so if I find the channel idle, there is only a 10% chance that I indeed transmit, and 90% chance I wait until the next time slot. This obviously reduces the collision. That's why overall, the throughput curve goes up. 0.5 persistent, 0.01, 0.01. So as we reduce the probability of sending P, the throughput is going up simply because we are reducing the chance for collisions. But my last comment before we finish this topic, do you think this trend will continue forever? So if this probability becomes 0.001 or 0.00001 and so on, as we reduce the probability P in P persistent, as we reduce the probability P, is it true that the throughput will continue to go higher? The answer is no. Obviously, if that probability P becomes too small, it means that we're also not sending enough, right? In the extreme case, imagine that probability P becomes 0. In this case, I'm not sending at all. So what are we delivering here? Nothing gets successfully delivered. So this is the trade-off. So as you notice, if the probability P for sending in the context of P persistent, if the probability P is too large, we're getting too many collisions and this reduces the throughput. But if the probability P is too small, this will also reduce the throughput, because not because of the collisions, because we're not sending, right? We're not sending enough. So it is maybe best that the probability P is somewhere in between, right? So not too large and not too small. So let me finish this video, and in the next video we will talk about a specific multiple access protocol for wireless LANs. See you then. Assalamu alaikum wa rahmatullah.